Okay, this example looks at the gradient of y equals x cubed. Now this is the bookwork definition of the gradient, the derivative at the point x, which tells us the gradient. This is the definition. Here's what it is in terms of a picture. You've got this triangle here under the curve between P and Q. This point here is f of x, that's the y. You can replace y by f of x, just notation. Q is just a little bit along a distance h, so the x point for Q would be x plus h then. And then this point on the curve would be f of x plus h, wouldn't it? That's the output when you input x plus h. That would be the y value at Q. So the gradient then would be the difference between the y's, fx plus h minus fx, divided by the difference between the x's, which is x plus h minus x. And you can see the x's cancel here, so you could just write x and h underneath rather. So let's just put the h in there. So that's what we've got. So that's the formula, and you can see that that's the gradient of the triangle at the point x. And when you take the limit, as h tends to 0, you're getting smaller and smaller triangles. This limit values tend towards the value of the tangent. So without further ado, because it sounds very confusing if we think about it too much, let's just do this example and see what comes out. We want the gradient of y, the curve y equals x cubed at the point x. Okay, so fx plus h, or fx plus h, that's y equals, this is the y, and there's the input value. So something goes to something cubed, isn't it, is the rule? So something cubed. And fx, of course, is equal to x cubed. This is the curve, y equals x cubed, and then the something goes to something cubed here. Better expand this bracket so it's x plus h. X plus h. Oh, we could use, let's use Pascal's triangle. You may not have seen it before, but instead of doing all the algebra, what you do is you draw a triangle, like so. But you might not have seen Pascal, so let's just do the algebraic way, because everyone knows that way. Slightly longer it will take, but let's just do it. Here we go. That's x plus h cubed. So look at this bracket first of all. 4 lines for a pair of brackets in this way. X squared plus xh plus hx, so that's 2 lots of hx, plus h squared. That's those 2 brackets expanded, and it's that times the x plus h. So here now you've got 3 for the first, 2 for the first, 2 for the second, and you're going to have 2 for the third, aren't you? So it's going to be 6 terms. So we've got x cubed plus x squared h, or hx squared, same thing, plus 2hx squared plus 2h squared x. Then the last one, plus h squared x plus h cubed. So what have we got then? We've got x cubed plus 3 hx squareds, and then 3h squareds x's plus h cubed. That's it. That's that thing expanded. Now we can look at the limit. So I've just managed to put this right at the bottom of the drawing, so I'm going to move it up to give me some more room. So apologies for that. Let's just move it up. Then we've got a nice bit of room then. Okay, so now let's have a look at it then. So we've got that, that's fx plus h. So we've got that component there. Now we just take it away from f of x and divide by h, and that take the limit. So f dash then, let's write out that formula, is equal to the limit, h tends to 0, of the fx plus h, so write that down, minus the f of x, remember the formula, which is x cubed, over h, wasn't it? And these cancel, and there's an h common on top, limit h tends to 0, 3, see the h common here on these 3 terms, so I'm going to take an h outside the bracket, and it will be 3x squared plus 3hx plus h squared on top, and the h underneath. And the reason we took an h out as common on top is because we can cancel it now with the h underneath. So that's the algebra. So that's simply equal to the limit as h tends to the 0 of 3x squared plus 3hx plus h squared. So that's equal to then, as h tends to 0, this will tend to 0, won't it? 0 times anything is 0. 0 squared is still going to be 0, so it's just left 3x squared. So that's the derivative then. Call f dashed x the derivative at x. So the derivative of x cubed is 3x squared, using, from definition, the limit formula. So if you look at the example just finishes off for it then. If you take it x equals 2 then, can we work out the limit of the curve fx equals x cubed? So we would have the point f of 2 is equal to 2 cubed is 8. So the point on the curve would be p to 8, and f dash, the tangent to that value, f dashed of 2, would be 3 times 2 squared. 3 fours are 12, so it's quite a steep gradient. So that point in the cubic curve, if you were to draw it, like so, that's the cubic curve. Say it's here. There's P, the point 2, 8, say. Badly drawn curve, I know. And then there's the tangent, like so. And it has a slope of 12. So if you're drawing a triangle, any triangle on this straight line tangent, you'd have a gradient of 12. If you're looking at another point on the curve, say, if you go on the other side, say at -3, say here, and you come down here, say, like so, and you wanted to find out that tangent, -3. So if we put in -3 into f of x, so let's just do that here, x equals -3, f of -3 would be -3 cubed, wouldn't it? And that would be -27. So I've managed to draw my cube curve completely wrong. A bit of a shame. So it's not there at all. So apologies for that. I was thinking of x squareds for some reason. So let's just draw it in again. So the cubic curve comes down here, like so. And then there's -3, say, and there's the slope. See it? At -3. So there's the -3. The value of y is -27. So there's the point, call it P dash now. If we wanted the gradient of that, we'd have f dashed of -3 would give the gradient of that value. And it's 3x squared, wasn't it? And the x value is -3. 3 9s are 27. Positive, so really, really steep straight line there. Really, really steep. 27.